right. Thanks a lot, Danielle. Thanks for having me for this very nice seminar series, online seminar series. I'm very honored to give a talk today. So it's a joint work with three other people. Chia-Hui Chen is in Kyoto in Japan. Yuria Eraslan is in Rice, but she ha also has a cross appointment at Osaka. And Junichiro Ishida is also at Osaka. So we are kind of sort of getting together to talk about this research idea, and then happy to talk about this today. So this is my oops, this is my first time to start the talk with a quote. Let me try. Um, this paper by three people, they say the following. The latest COVID-19 vaccine monitor reports 31% of the public say that when FDA-approved vaccine is available to them for free, they will nevertheless wait until it has been available for a while to see how it's working for other people before getting vaccinated themselves. Several years ago, it's almost like a past event that, this COVID kind of was, influencing everyone in this planet. But at the beginning, well, at least at the beginning of this vaccine, at the beginning, of this vaccine period, we had this kind of, we faced this kind of uncertainty. We wanted to see how it's going to be working, right? So this is the kind of phenomenon that we want to understand, especially from the viewpoint of the society, how we should manage this kind of incentive to collect information and finally to make a better decision. So, as in this quote, our main application of this talk is this COVID vaccine vaccination campaign, although we can also imagine some other applications. And in some sense, maybe other applications in the end might better fit. But anyway, as a kind of motivating talk, this is probably the best application. So let me try to fix this one. Okay, so imagine, we have this new vaccine. At the beginning, we didn't know whether they are, first of all, effective or not, and whether they're going to have some severe side effects. In the end, there was almost nothing to worry about, but we didn't know that ex ante, right? So we faced this kind of uncertainty. To know the answer, citizens' experimentation is key. Yeah, it's a key to collect the information. But it's kind of strange, right? We want to know whether this vaccine is a good one or not for citizens, but we need citizens experimenting to know this answer. And this kind of sort of strangeness also carries over to individual citizen side. So imagine that you are one of those citizens, and say, imagine you're patient enough. Do you want to take a shot today or not? If you take a shot today, there is some benefit. Maybe you can go abroad without any hesitation. But there could be some side effects, for example. Yeah, or you may get vaccine. The virus somewhere. Yeah. You can also wait until tomorrow. In that case, you cannot go abroad today. Too bad. But the good thing is that you probably have more information tomorrow. So you're going to face the same kind of decision problem, but probably with more information. So there is some, option value of waiting, yeah, because you can make a better decision by waiting. And importantly, this decision depends, first of all, whether you are patient or not, and also how much information or what kind of information you can expect tomorrow. So this implies that from the authority's viewpoint, let's imagine the authority is a benevolent entity. This authority faces the following trade-off. Imagine that this authority is at time t. Giving more information at time t makes the citizens' decisions better, definitely, because people can make more informed decisions. But if the authority promises that this kind of information will happen at t, or if people expect that such information will come at t, then this is going to disincentivize the experimentation motif at t minus 1 or even before, yeah, based on this kind of story. And hence, less people experiment, hence less information to the government, to the authority. Yeah. So it's a kind of trade-off, yeah, whether to wait more of these period T better decision or information collection before that. Okay. So we want to understand, what's going to be the optimal mechanism in this case, what sort of inefficiencies are kind of unavoidable to achieve this second best mechanism. So this is basically a dynamic information design with a collective experimentation. Yeah, we can imagine some other applications such as technology adoption and some other things. So before or without going to the formal model, which comes in a few slides, let me try to give some flavor of the main results of this paper. So we have two results. First of all, we're going to show that full disclosure is not necessarily optimal, as you can probably guess from my last slide, because this full disclosure may result in huge delay in social learning. Yeah, many people just wait until until they get some information. But if no one experiments, of course, such new information will not come. And this kind of problem will be severer if people are more patient. So that's kind of one result, one observation. And based on this, next we're interested in the characterization of the optimal mechanism. So if full disclosure is not optimal, and also like there is a separate argument showing that no disclosure at all is not optimal either. We are somewhere in between typically. What would be the kind of optimal partial information? Yeah, partial disclosure. So this second result basically tries to characterize what are the key properties of this optimal mechanism. So first of all, we're going to show that the optimal mechanism actually takes a very simple form. We call it a kind of binary property. So at each period, given whatever history by then, the principal only sends one of the two messages essentially. Either the principal says, let's continue, meaning that, the principal recommends some, basically, principal makes people relatively more optimistic than yesterday, so that some chunk of people want to want to take shots today. Or the second message, terminate message. This terminate message basically says that, or makes the citizens more pessimistic than yesterday. And basically, they get more cautious and they stop experimenting. And that one of these two messages would be enough. Even though, of course, if the principal wants, he can send many other possible messages. So that's kind of simplicity of the optimal mechanism. The second property is what we call a termination property. So let's imagine that the principal sends this termination message at period t. In principle, it's possible that period t plus one, the principal again, hey, let's continue a bit more, get the vaccination and see what happens. But this is not what should happen in the optimal mechanism. What should happen in the optimal mechanism is that once the principal sends this terminate message, then it's basically a terminate. I mean, as this word suggests, it's a termination forever. So only if principal continued sending this continue message, this experimentation will continue. Okay? And once he stops, everything stops since then. So that's the second property of the optimal mechanism. The third property, in some sense, I think is the most interesting, is the kind of caution property. So as I said, full disclosure, when full disclosure is not optimal, then the question is what kind of partial information is optimal. Yeah, meaning like what kind of information the principal should hide and what kind of information he should reveal. The third property is about that. The third property basically says that this termination occurs for sure, first of all, if the principal observes the conclusive bad news. Um, so, if the principal is sure that it's not a good vaccine, then he stops. It's not surprising, but that's one property. And the second property is that even if the principal is not that pessimistic, or actually even if he's more on the optimistic side, still the principal introduces this probability of terminating it. Even though principal is optimistic, he commits to terminate this vaccination campaign. And that means that, okay, so if the principal says continue, this means that the principal must be very optimistic. Yeah? If the principal says terminate, then either it is really a bad state, or it's a kind of good state, but principal went to the second scenario. Yeah. So kind of partial information that should be revealed to the citizens. And the reason why the principle introduces this kind of overly cautiousness is because that will give the information less precise. That will make the information less precise, and hence can make earlier citizens more incentivized to take shots earlier. Yeah, so that's a kind of intuition. But I think it's a bit informal here. So let me try to go into the model to explain them more formally. So as I mentioned, this paper belongs to the kind of intersection of two literature. One is the strategic or collective experimentation, and the other is this information design. There are some papers which are very closely related, but for the sake of time for today, let me skip this. I'll be happy to come back if you want later on. Okay, so that's it for the introduction. And as I said, any question is welcome at any point of the talk. So please feel free to step in. Yeah, it's okay. All right. So let me explain this model. So we have a discrete time set up with some deadline. Let's simplify the setting for today. We only have 2 periods. Yeah. And there is one good, imagine this vaccine of unknown quality. So the quality is either 0 or 1. And here, quality 1 is bad, actually. So you can imagine this omega is a kind of state about the side effect. Okay, so omega equal 1 means that we're going to have side effect, like severe side effect. And 0 means it's free from that. Okay. And the prior for a bad state is mu1. The consumers or citizens are heterogeneous in terms of the valuations they get from this vaccine. And it's a number between 0 and 1. They are distributed according to some distribution. For simplicity, today it's a uniform distribution. It really doesn't matter. You can imagine any kind of continuous distribution on 0, 1. The payoff of a person, of a consumer, of a citizen, is the following. So if he consumes this vaccine at time t, so first of all, that is discounted as usual, and he gets this gross payoff v, yeah, by going abroad. But if it's a bad state, then he suffers from a side effect. Omega is either 0 or 1, and v is between 0 and 1. So if omega is 0, then everyone wants to, take it. While if omega is 1, then no one wants to. Yeah. And this vaccination is a kind of irreversible decision. So if you haven't took a shot, then you can stay in the market, and at some point you can take one. But once you take it, then you basically you're over. Yeah, you leave the market. In reality, of course, sometimes we had to take multiple shots, but let's simplify that one is enough, yeah, to get vaccinated. The principle we already decided. So we assume it's basically a kind of normative question that we want to study. So let's imagine a benevolent principle, which also has a commitment power. So we are in a dynamic information design framework. Now, the authority basically principal receive a bad signal. So it's a kind of so-called conclusive bad news model. So he may receive some bad signal, like a severe side effects report, at time t with probability which is like this. So omega times p of nt. So NT is the mass of consumers who consume the vaccine, who consume the good at T. Okay. So if there is no one consume it, then P of 0 is 0. So there is no chance of getting any signal. Even if there are some people taking a shot, so P of NT being positive, say, if the state is good, omega is 0, then there's no chance of getting a side effect. Um, Only if omega is 1 and there are like some mass of people taking a shot, there is this probability that the principal gets a bad signal. And it's a conclusive bad signal because this bad signal can only happen in a bad state. Yeah, so as soon as the principal gets such a bad signal, it reveals that omega is 1. Yeah, so in that sense, it's a conclusive news. But if the principal didn't get a bad signal, it could either mean that omega is actually 0, or omega is actually 1, but for some reason this bad signal didn't arrive. Yeah, so one of these two possibilities. So if there is no news, the principal basically keep updating. Yeah, keeps updating. Okay. And so that's the kind of information structure of the principal. And the principal can give some message to the agents, to the consumers at each period. And for the consumers, this principal's message is the only source of information. Yeah. In reality, of course, they can, people can get some information from peers or from, I don't know, from SNSs and other things. But for simplicity, let's shut down all the other information sources. It's only coming from the authority to make the problem basically belong to this information design framework. Okay. All right. So let's see what's going to happen in this problem. And with two periods, nice thing is that we can write down everything. Yeah. So in period one, this is the kind of events that would happen. Um, at T equal one, the consumer, they are heterogeneous, so they have different V's. So the consumer with each V decides whether to consume the good, yeah, whether to take a shot. And basically, I don't prove this, but there is a kind of skimming property in equilibrium. So there will be some threshold type, V1. I explain how this V1 is determined. But there is some threshold type V1 above which they consume and below they. Oops. Okay, so we have this V between 0 and 1, right? And there is this threshold type V1, okay? And the period 1, or V1 could be 1, yeah, meaning no one consumes, uh, or V1 could be 0, meaning everyone consumes. But if V1 is here, then everyone above will consume, yeah? And this V1 is an equilibrium object, okay? And everyone below B1, they don't consume today. They wait until tomorrow. Yeah, T equal to. Okay, so far so good. So at the beginning, like consumer, yeah, basically behaves without any information from the principal. And now, given that this mass of people consume, right, this 1 minus V1 measure of consumers consume. So given this, now the principal can potentially receive some signal, yeah, some bad signal. Okay. And once again, it's a conclusive bad news model. So if the principal receives such a bad signal, like a side effect report, then his belief jumps to one. Yeah, he becomes sure that it's a bad state. With the other probability, the principal gets nothing, like gets no information. And in that case, because there was no bad news, the principal gets slightly more optimistic, but not, not entirely optimistic. So his posterior would be either this conclusive bad kind of case, or this slightly more optimistic than yesterday kind of posterior. And this posterior can be computed in this way, right? So it is so the no news will come either because it is indeed good state, omega is zero, right? Or it is omega equals one, but in that case, the probability of bad news arriving is P of N1. N1, sorry, N1 is this measure, yeah? N1 is this measure. So 1 minus P of N1 probability, no news happens, even though um, it's a bad state. So that's the probability in denominator, and then numerator is the probability that on top of that omega is indeed one. Yeah, so it's just a conditional probability computation. So far so good. Yeah, that's what happens in period one. Now let's move on to period two. So this theta one is just the principal's information. Yeah. So he didn't still share that information with the public. So at the beginning of this period too, the principal has this option of sharing some information, or more generally, the principal can send some message, and we focus on public message to the consumers. Okay. And based on a standard logic in Bayesian persuasion, this message from the principal, we can think of this basically as the posterior that the consumers should possess. Yeah. So this mu2, this posterior can be any number between theta lower bound 1 and 1. Yeah. So if the principal basically reveals that it's, like, for example, he got a conclusive bad news, then the posterior should be 1. Yeah. If the principal reveals that he didn't get any bad news, then the public also share this optimistic posterior of theta lower bound 1. If the principal sends more nuanced message, then the posterior will be somewhere in between. Yeah. So that's what he can do. Okay. Let's imagine that such a posterior mu2 is given to the public. Yeah. What happens next? Well, it's again in a very simple two-period situation. So this is the last period of the game. Each consumer decides whether to take a shot, and that's the end of the game. So if this consumer has type V and the posterior is mu2, then the consumer consumes if V is greater than mu2, and otherwise he doesn't consume. Yeah. So let me draw another line. I should make it thinner. Oops. Can I? There we go. I drew the same thing here. So V between 0 and 1. But above V1, they already took a shot at t equal to 1. Okay, so the remaining guy is everyone below V1. And now if mu2 is here, so maybe I change the color. If mu2 is here, then any v between mu2 and v1, they will take a shot. Yeah. So they are relatively optimistic, so they take shots. And those people below mu2, they don't take a shot. Yeah. Mu2 is not optimistic enough for them. So, and that's the end of the game. Yeah. If we have three or more periods, then, based on this red region who take a shot, the principal gets even more information, yeah, whether a bad signal or not, and then give some signal to the public. Some citizens take shots or not, and so on and so forth. Yeah. But for today, it's just for periods. Okay. So far, so good. So what the principal can do, the principal strategy, and we assume commitment power. So the principal commits to whatever strategy at the beginning. What is his strategy? Well, his strategy is a mapping. Yeah. Depending on his information, which is either he himself is relatively optimistic, or he already knows that it's for sure a bad state. He sends some signal. He sends this posterior to the public. Yeah, what kind of posterior they should possess with kind of base consistency requirement or kind of low iterated expectation kind of constraint. Yeah? So he cannot sort of tell a lie, yeah, in a systematic way. So it can be if you want, it can be described in the kind of table format. Yeah. So if what the principal knows is that it's for sure already a bad state, then the principal may send either mu2, mu2 prime, or mu2 double prime with certain probabilities. Yeah. If theta one is theta one lower bar, so if the principal is more optimistic, principal didn't get any bad news, then again, like he can choose what kind of distribution of the messages he sent. Yeah. And this first message labeled as mu2 means that given those probabilities here and there, if we apply Bayes updating, Bayes rule, then this mu2 should be indeed the posterior for the omega to be 1, right? So that's the kind of consistency requirement, okay? And which implies in particular this kind of condition. But anyway, there is some kind of base consistency requirement. But the point is that the principal has to choose this mapping or this table, yeah, mapping from each of the information he has to the distribution of the messages to the public. Okay. Okay, so this is the kind of sequence of events and the principal strategy. And what about the agent side or consumer side? As I said, at each period, there is some threshold type, yeah, above which people take shots. And the question is how this V1 is to be determined. Yeah. So this first period threshold, how it's determined? Well, it's based on the kind of indifference condition, right? This guy at V1, he should be indifferent between taking a shot today or wait until tomorrow. If he takes a shot today, then he gets this gross payoff V1, but with probability mu1, it's kind of a bad state. Yeah, so the expected payoff is V minus mu1. What happens if he doesn't take a shot and wait until tomorrow? If he waits until tomorrow, first, the payoff is discounted by delta, of course. And then what happens will depend on this mu2. Yeah. So, for example, say V1 is here, and for whatever reason, he didn't take a shot in period 1, so he waits until period 2. The period 2 posterior or period 2 message could be either here, like mu2 could be here, mu2 could be here, or maybe mu2 could be there. Yeah, we don't know. And in the first two cases, if mu2 is here or there, yeah, in this case, the V1 is higher, right, relative to those 2 points. So if the posterior message, like a second period message, is either of these two, then this V1 guy will take a shot, will consume in period two. However, if mu2 turns out to be this, so by waiting, there was new information to the principal, and the principal says, "Gee, there was some side effect report, so let's stop it." Yeah. In that case, of course, V1 also wants to stop it, and that way, his payoff is either this V1 minus mu2, or zero. Yeah, whichever is larger. So he has a kind of kinked convex payoff function in period two. Yeah. So this V1 guy compares this first period consumption, second period consumption, and takes the better one. Okay. So okay. So maybe I was a bit too slow. So let me try to catch up a bit. But if yeah, okay. Perhaps silence just means that you're happy. In that case, I'll be happy to continue. I don't know how to. Sorry, just a moment. I don't know how to move on to the next page. Is that is it freeze? Okay, okay. Do this way. Okay, so now let me describe the main results of the paper. And the first one is about the suboptimality of the full disclosure and also no disclosure. So by no disclosure, I mean that it's basically a beta such that the second period posterior is the same as the first period posterior. Yeah, meaning that there's no information revealed in period two. If everyone knows that in period two, no information will be revealed by the principal, then of course there is no reason to wait until the second period. So those who want to take shots in first period, they just take it. And that's it. Yeah, second period, the principal gets some information, but he doesn't release it. Yeah. So V1 will be simply mu1. But well, I don't prove this, but we can show that it's not optimal quite easily. The second scenario, or second kind of candidate strategy is full disclosure. Yeah, whatever information the principal gets, this theta lower bound 1 over 1, right? The principal reveals it kind of truthfully and fully to the public. If that happens, then the consumers have some incentive to wait. Yeah, and as this delta becomes higher, and as people become more patient, there'll be more incentive to wait. And actually, if we go back one slide. Why I cannot go back one slide? We go back slide here. So if delta is close to 1, yeah, then we can easily show that this right-hand side is definitely greater than the left-hand side because mu2 has the mean average mu1. But this one, we're considering a convex function, while here it's a linear function. So we should be, the right-hand side should be larger if delta is close to 1. So if, meaning that if people are extremely patient and full disclosure is promised, then no one experiments. Yeah. And obviously that's not a good idea because the principal will not be able to get any information in that case. So it's of course just an informal argument, but I think the result is quite intuitive. First of all, no disclosure is always suboptimal, and for full disclosure, if people are patient enough, it's also suboptimal. Okay. Excuse me. The intuition I already explained, so I'm going to skip. So, so in that sense, reasonable sort of parameter space, we expect to have some interior optimal policy. The question is, what kind of interiority we want to have? It's a dynamic Bayesian persuasion or information design setting, so we can potentially have some random messages. We can have some delay. What would be what kind of information the principal should hide? Does he like should he hide the kind of good information, or should he hide some bad information? Yeah, from the citizen's viewpoint, should they expect false positive or false negative? Yeah, so that's the kind of next question that we want to understand. Okay. Okay, so before giving the kind of answer to that question, let me explain how we can tackle this problem. So two-period problem, it's actually not too bad. We can try to solve it in a relatively brute force format. But imagine that we have like 10 periods or undetermined general T periods. How to solve it is more, a bit more problematic. So the kind of way we tackle this problem is the following. So basically, we're going to choose this beta, the principal's disclosure strategy, and also this threshold type V1. Of course, this threshold type V1 fully determined once B is determined. So in that sense, it's just one of them rather than both. But it's going to be useful to denote this way. Um, and this V1 has to satisfy this threshold condition. And this objective of the principle is social welfare. Yeah. For those who are above V1, they consume in period one. So this is their payoff. For those between or below V1, depending on mu2, they consume or not. And so this is the kind of second period welfare. Yeah. And we have this base consistency thing. So how to solve this problem? Well, we can solve it in two steps. The first step, let's fix any V1, any feasible V1, and only focus on this beta side. More precisely, let's try to find the optimal beta among those which induce this fixed V1. Okay. So we kind of target whatever threshold type in period one, and we only look at those policies. Okay. What is the optimal one? Now, once we could solve this problem, step one, for each V1, then this V1 can be optimized in the second step. Yeah, the second step is just a one variable problem, so it's not that complicated. Okay. The first step problem is still kind of complicated, right? Because we have to look for all possible betas. Yeah. But what is that in this step one, actually, the principal can try to maximize the social welfare by giving more information. So remember, the reason why the principal doesn't want to potentially disclose too much information is because of this weighting motif, right? If the principal gives too much information or promise too much information in second period, in the first period, less people will experiment. Yeah. But think about this step one problem. We only focus on the betas which induce the same V1. In other words, we are kind of abstracting away from this weighting problem, a free riding problem. Yeah. So within this class of beta, there is actually no concept of the preferences between the principal and the agents. So within this class of betas, actually is always preferable for the principal to give as much information as possible. And that will be useful to understand the solution of this step one. Okay, do you understand the intuition here? Is it okay? Okay, so having this kind of intuition in mind, try to give a graphical solution to the step one problem. So the formal proof is in the paper, but I can give a sketch using the graph, the same kind of graph as before. So let's say I have V here, and that's between 0 and 1. Okay. So for this problem, yeah, let's fix whatever V1, the target V1, yeah, and any beta that induces V1. So not necessarily the optimal one, yeah. Okay, and we have V1 somewhere here. Okay. And I don't know where's mu1, but well, mu1 it doesn't really matter, but probably mu1 is somewhere here. Yeah, because of the option value, v1 is perhaps strictly greater than mu1. And the second period, mu, so mu2, um, I don't know, like, we fit whatever perhaps optimal data. So let's imagine whatever disclosure strategy here. So to understand what is possible, so one is here, and theta, this remember, this theta lower by one, that is the kind of lowest possible belief the principal can induce, right? By truthfully revealing what he has in mind, what he has as an information. Okay, so, and any point in between is feasible mu2. Okay, so let's imagine that say mu2 is either here, here, or I don't know, here, here. Yeah, say 4 possible mu2s. Yeah. I'm going to claim that this is not optimal, and we can do better. Okay, so how we can do better? Yeah. So let's look at this leftist point. Let's mark it as red. This guy. Okay. So this is a relatively optimistic information, right? Or actually, most optimistic among possible information from the principle. Yeah. Instead of doing this, let's split this point into two. One is this theta lower bar one, and the other is this exact threshold V1. Okay. Meaning that the principle gives more precise information. Yeah. So instead of this red point, it's going to be either this. Sorry, I should change the color perhaps. Oops. It's going to be this. Let's use orange here or there. Okay. So we have more. The principle gives more precise information. Yeah, that's good in general, especially if you imagine some value type here. Before with this red information, this here, let's call it V star. This V star guy just takes a shot. But with this more precise orange information, he takes a shot if this is kind of theta lower bar, but he doesn't take a shot if it's this upper one. So this V star guy was this kind of operation. Anyway, no one gets hurt by this. Yeah, it's just a more information possible. But if we look at this V1 guy, actually he doesn't care because V1 guy before split it was this red point. So with this red point, this V1 guy will take a shot in period two. Yeah. After this splitting, this is right over at least weekly below V1. So from the viewpoint of V1, it doesn't matter. It's a more precise information, but in either case, they shot uh, if he waits till period two. So this more information doesn't increase this V1 guy's option value of weighting. Yeah, the right-hand side of this is. So this red splitting of this red point to two orange point is generally beneficial to society, but it doesn't change V1. In particular, such a new policy in the same class of V, yeah, which induce the same V. Okay, so that is welfare enhancing, yeah. And the same thing here. So if we have this second point here, we can split in the same way. So It's going to be splitted either here or here. Yeah. And again, V doesn't care, but some other people are better off. Okay. So what can I say? I can say that this original red ones are not optimal because there was a better policy. Better policy basically has all the mass either here or I should, I'm not good at colors. Either here or there. Yeah, there's no point in between. I should let me draw another line to be clear. Yeah, so the better one, we have either the theta lower one or one. Okay, either of these two. As long as we are looking at the points to the left of B1. Yeah. So we haven't still talked about the right one. So let's now talk about the right one. So let me use the different colors. The green guys here. Okay. So those green guys, what should we do? Well, those are kind of pessimistic, like too pessimistic information in the sense that if V1 waited until the period 2 with those green information, like mu2 closer to 1, V1 doesn't want to take shots. Yeah. Actually, remember that um, those who remain until period 2 are those people here, yeah, the below V1. Those people above V1, they already took a shot in period 1, so they are already gone. Yeah, they are out of the market. So among those green people, including V1, if the mu2 realization is either of these two green points, then they don't take shots anyway. Yeah. So the fact that we have two green points here and there doesn't matter at all. We can merge these 2 points into one. It doesn't matter. In any case, no one takes a shot in period 2 if the realization is in this green region. Okay, so instead of 2 points, like in this second graph, we can have a single point. I don't know, it's somewhere, but somewhere here. And it's not strictly improving, but at least it doesn't change the welfare. So we now have the simpler one, the third one. Yeah. And to have a binary support, there is one more step to merge this guy and that guy to have somewhere to have another point like here. But it's the same logic. But the point is that to the left of V1, we can split into theta lower bar and V1, and any points above V1 we can merge into one. Okay, so that's what we can do. All right, so I hope it's kind of convincing that within this step 1 problem, we should have these kind of supports. Now, what we can say? Well, we can say that of the optimal is so after merging these two as well, yeah, into one, we have basically 2-point support of this beta, yeah. One is this guy, the lower bar one. And the other, we don't know what is the number, somewhere above V1. Okay? Only this binary support. Yeah, so that's the kind of binary proof that we wanted to show. So here, the repetition of the statement. Yeah, so we just have binary support. So that's one of the properties. And about the properties, well, imagine that we are already we are here. Yeah, the principal revealed this information, which is this. So I think I call it the theta upper bar one, and this is theta lower bar one. Right? Given theta upper bar one in period 2, as I said, no one takes a shot. The game is over for 2-period case, but if you imagine 3-period or 4-period, in case this pessimistic information is given, basically no one takes a shot in period 2, and hence principal gets no information. And without any information, principal has nothing to release. So basically, this just continues. So this will basically a kind of termination. Well, it's quite informal. I'm skipping some, key parts of the proof, but I think it can be. What is more perhaps interesting is about this caution property, the third property. So remember, one of the support is this point. What is this point? This is the point that the principal basically reveals that he didn't get any bad information. Yeah, it's a kind of same posterior as the principal, meaning that if the principal reveals that information, the public basically knows that that is the case. Yeah. So that's the kind of last caution property. Oops, sorry. Yeah, here it is. So the meaning. So okay. So in order to induce this kind of posterior to the public, it's necessary that the principal never continues in case he gets bad news. While he may stop with even if the principal is relatively optimistic, and that's why this stopping or termination posterior is strictly less than one. So that's what we call a caution property. Okay, so just to recap, I think I'm almost at time. So in the optimal mechanism, we have three properties, and that's true even if we have more periods. So the message can be just binary, and we have termination property, meaning that once we stop experimentation, then we stop it forever. And the third one is a caution property that even if the principal is relatively optimistic, he might want to stop. Yeah. And how likely he wants to stop, it depends on how much this earlier experimentation is important, or how severe this free riding motif of the agents is. And then like we can talk about the choice of the threshold type V1, but I think for the sake of time, let me skip. And let me conclude. So here, like we studied this problem of incentivizing experimentation of the society, and it's important to essentially optimally control this dynamics of the threshold types. In other words, if we can fix this sequence of threshold type realization, the remaining part is basically the welfare maximization. So the principal should just disclose as much information as possible. And the consequence is this simple binary mechanism with termination and caution properties. So I'm done. Thanks a lot.